This is Learning Assessment Problem 714. In this problem we have a second-order transient circuit caused by the switch opening at time 0. The problem-solving strategy here will be that of second-order transient circuits. We are requested to determine the current I of t for time greater than 0. That is the current flowing into the capacitance. So the first step would be to determine the initial conditions for the two energy storage elements. So we'll do this calculation just before the switch opens, so the switch is configured as it's indicated in the circuit drawing here. We'll assume that steady state prevails, therefore there will be no voltage across the inductor, and the inductor will look like a short circuit under that condition, and the capacitance will look like an open circuit because of the steady state condition. No current will flow in it. So we can do a KVL summation of voltages. Let's label some names here. We'll have VC, V sub R, So performing the summation of voltages, we have minus 12 volts plus IL at 0 minus times 6 ohms Performing the KVL summation, we'll have minus 12 volts plus 2 ohms we'll have minus 12 volts plus 6 ohms times IL at 0 minus plus V sub L at 0 minus is equal to 0. So that's the loop around the right-hand portion of the circuit. We just established that in steady state the inductor voltage is 0. So we obtain then that IL at 0 minus is equal to 12 volts divided by 6 ohms, and that's equal to 2 amperes. Since the inductor looks like a short circuit, V sub L at 0 minus is equal to 0. This yields also that VC at 0 minus is equal to 0. Then the switch opens at time t equals 0. So we've established the initial conditions, the initial current in the inductor, and the initial voltage on the capacitor. Now we'll proceed to analyze the circuit for time greater than 0. Now at t greater than 0, the switch is open, and we have the resulting circuit shown here. The voltage source has been removed by the opening of the switch. We again have the capacitor voltage VC plus and minus, voltage drop across this resistor V sub R, a voltage drop across this resistor V sub R, voltage across the inductor V sub L. Now at t greater than 0, the switch is open. In the circuit we have this resistor V sub R. We have a capacitor with a voltage V sub C. Inductor with a voltage V sub L. And we're going to consider a loop current here, I of t now. And that's the desired current, that current flowing in the bottom line of the circuit. So we have a series RLC characteristic equation of the form S squared plus R over LS plus 1 over LC is equal to 0. The R over L ratio for this circuit is equal to 3 ohms divided by 2 henries, and that's equal to 1.5. The 1 over LC term is equal to 1 over 2 times 1, which is equal to 0.5. So our characteristic equation is S squared. So our characteristic equation is S squared plus 1.5S plus 0.5 equals 0. The roots of this are minus 1.5 plus and minus the square root of 1.5 squared minus 4 times 0.5 divided by 2. And solving, we have S1 is equal to minus 1, S2 is equal to minus 0.5. So therefore, the general form of our current expression will be I of t is equal to K1e to the minus 1t plus K2e to the minus 0.5t. So we have two coefficients, K1 and K2, to determine, so we need a second equation. In K1, K2. We'll consider it We'll consider a KVL expression around the loop. We have V sub C plus V sub R plus V sub L sums to 0. And we'll consider T equals 0 plus, just after the switch is opened, VC at 0 plus is equal to VC at 0 minus by the continuity relation for a capacitor, and this is equal to 0. So in the expression and for the summing of voltages, the VC goes to 0, and we just have that VR at 0 plus is equal to R times IL at 0 plus. This is equal to 3 ohms times 2 amperes. That relies on the continuity of the inductor current across the switching event, and that's equal to 6 volts. So in this KVL equation, we've established that V sub C is 0. We've now determined a value for V sub R. This is at the time 0 plus. Now we'll look at how this may help us in determining the value of V sub L at 0 plus. So at t equals 0 plus, we have VR at 0 plus V sub L at 0 plus is equal to 0. And this gives us that the 6 volts for the V sub R is equal to V sub L at 0 plus is equal to 0. So now at t equals 0 plus, our KVL expression becomes V sub R at 0 plus V sub C so at t equals 0 plus, our KVL equation becomes V sub R at 0 plus V sub L at 0 plus equals 0, which gives us that 6 volts plus V sub L at 0 plus is equal to 0, or V sub L at 0 plus is equal to minus 6 volts. Then recall that V sub L of t is equal to L dIL dt. It's related to the derivative of the current flowing through that inductor. So V sub L of t is going to equal L d by dt of our assumed form of the current, K1 e to the minus 1t plus K2 e to the minus 0.5t. This is equal to 2 henries times minus 1 K1 e to the minus 1t minus 0.5 K2 e to the minus 0.5t, or VL at 0 plus is equal to minus 6 volts from the KVL equation, and this is minus 2K1 minus 1K1 minus 1K2 from our assumed solution format. So we can say that I at 0 plus is equal to 2 amperes from the initial condition on the inductor current, and in our assumed form of the solution this is K1 plus K2. So in a matrix format of these conditions we have 1 minus 2, 1 minus 1 for the coefficients of K1 and K2, K1, K2, and on the right hand side we have 2 amperes and minus 6 volts. And solving this matrix equation, you'll obtain K1 is equal to 4. That goes along with e to the minus 1t exponential term, and K2 is equal to minus 2, which is associated with e to the minus 0.5t exponential term. Now we can take the K1 and K2 terms. Now we may take those K1 and K2 values and apply them to our assumed form for the current. I of t is equal to 4 e to the minus 1t minus 2 e to the minus 0.5t, and this is valid for t greater than 0. The form of this response is that of an overdamped circuit.